Okay, so I think if there's no other question, then let's start the lecture. Thank you, Rene.
Thank you, everyone.
Hi, everyone. Can you hear me?
Yes.
Great. So my name is Dmitry Mishkin. I'm a PhD student at CTU in Prague, and I'm a bit different from all the people who spoke about before me, because I never wrote any paper about RANSACs. I don't research them, but I use them every day. I do two-view matching for and some different kind of registration problems, local features. So, and of course, I'm very interested to put the very best robust geometry estimation model into like my framework. So, and I had just like this practical point of view. So, what is the best for practical use? And this is what I'm going to present. If you look at the papers, especially for deep methods, they say, okay, there are, in all papers, there is this kind of question, image where you have, okay, our correspondences are green and correct, and RANSACs are red and bad, or maybe without correspondence, but still. So, and you see that RANSAC is always the reddish one, and the deep network always is green. But is it so? So let's find out. So, and before having this tutorial, we discussed that we would like the large-scale benchmark for all kind of robust estimation problems, like structure for motion, fundamental and essential matrices, homography, PNP, rigid point registration, multi-instance estimation, multi-model estimation, so a lot of things. Then time passed. And 1 month before tutorial, we thought, okay, that's kind of enough to get fundamental and essential matrices, homography, PNP, rigid point cloud registration. And yesterday we check, okay, what do we have results for? We have 2U geometry, we have perspective transform, and we have rigid point cloud registration. So why is this kind of small subset of everything? And as it was mentioned before, the robust estimation benchmarking is hard. First, there are few data sets for RANSAC-like problems, and existing ones are mostly small. This means that one cannot train and evaluate deep learning method on existing data sets for the lots of problems. Or for some we can. There are data sets for them, but not for everyone. But okay, at best we probably can just benchmark all the classical methods, can we? But there is no common evaluation protocol. Like how should we do this? What is the metric? Would it be inlier ratio of output of like popular metric is number of correct inliers, which means number of inliers which are consistent with ground truth model. But imagine if you have some degenerate model output, so your inliers are correct, most of them, but the model is completely wrong. Is it good? Probably not. Percentage of success, which means like how do we measure success? Imagine how can we compare actually models themselves? It's not clear at all. Moreover, there is no training, validation, and test split. And there is kind of popular joke in reinforcement learning that this is a super good thing because it's socially acceptable to test on your training set. Unfortunately, the robust estimation data sets are the same. So there are some small data set and you have some ground truths, and that's all. People even tune the parameters of model not per data set, which is already quite bad. Like in ML community, it would be unacceptable. But moreover, you can even tune your parameters per the image pair or per problem, which means that you're actually training on your test set and then output results. And this is common practice. I don't want to point to papers, but a lot of them do it. There are often no fixed set of correspondences to use, which means that one can preprocess them one way or another, and to make a method he or she wants to win, like just willingly or just by mistake. So we present our benchmark collection, so-called. We haven't been solved all the mentioned problems. It is like very beginning, but we believe that we done kind of good step in this direction. The input data and the evaluation scripts are available to download from this repository. It's not yet well documented, but there are already some comments how to get and evaluate the model from OpenCV, for example, and so on. So you can evaluate your model or submit your results. So let's start. And let's start with fundamental and essential matrix estimators, which is this, can you see this pointer? Okay, so we have two-view geometry and ridges in motion, which means that the only motion we allow is motion of the cameras, and the rest should be static. Luckily, there is work which I also was part of, and which is will be presented on image matching workshop on Friday. We created a modular baseline to benchmark all the components of the structure from motion, and I will now explain how we do it. We take full data set, means like thousands or hundreds of images which belong to some landmarks seen like Sacré-Cœur or like Prague Castle or some other famous landmark. Then SFM like call map is run, and there is like very dense ground truth, like kind of ground truth model is obtained. Because there are a lot of images, this is kind of easy for SFM to register it very precisely. And this is used as a ground truth. Then we can have an image subset from this full data set up to just pair of image. And of course, you cannot recover ground truth from 2 images or from 3 images and cheat. Then one can do feature extraction, feature matching, filter these matches like by lowest second nearest ratio or something like this. Then estimate model by RANSAC, and then we recover pose and compare it as a kind of downstream metric. Like what do we care about when we do 3D reconstruction? Probably 2 things. One is how is correct all these camera positions and the point positions, and second is its density. We don't measure any density here. We measure pose accuracy. And there is this other thing which I covered by this gray thing which we don't touch here. And dataset is a phototourism dataset. It is a subset of Yahoo Creative Commons dataset, 30K images split in 2016s, and then split to training set and test set and validation set. It is the basis of image matching competition from previous year and this year, which is again in conjunction with CVPR workshop on image matching. So I invite everyone there. And so from these kind of images, you get this kind of 3D model. And here is some statistics. For training set, we provide everything like camera pose, calibration matrices, images, and for test set, only subset of images are provided. These are like full set from where there was ground truth 3D model reconstructed, and we provide only 100 images per each subset. And the question is, can we trust the so-called ground truth from Coleman because it may be biased and so on? The answer is yes. So we reconstructed a scene with three kind of completely different features. Handcrafted sift, superpoint, which detects corners, and R2D2, which detects whatever it likes as repeatable and matchable things. And if you increase number of images for the 3D model and measure the average distance, average pose error between them and like difference, first you see that it converges, and second, it's kind of consistent for all kind of features except superpoint, but it detects very little number of points, and this model is much sparser, but still is pretty consistent. And here is this mean. This is 0.39 degrees, and this is median error. So it's pretty stable and pretty precise for our metric, which is mean average accuracy at 10 degrees. And how do we do this? So we calculate by RANSAC or other evaluated method fundamental or essential metrics. Then we recover, if it's fundamental metrics, we then recover epipolar essential one by using ground truth calibration matrices. Then we recover pose with OpenCV function. Then we decompose these two components, which are rotation and translation, again into rotation and translation components each, because for the translation vector you still have a direction where you should translate, and then metric. And because we don't have metric reconstruction, we just take angular error, and then we threshold it at a set of thresholds, like at 1 degree, 2, 3, 5, and so on, and then calculate average. So this is mean average accuracy at 10 degrees. This is our final metric downstream. So now, as I said before, that by changing the correspondences as an input, one can easily manipulate the results. Thus, we, unlike for this local feature competition, we decided to fix the input correspondences. And how do we do this? So here is a benchmark of different local features. And as one can see that OpenCV Sift works quite well. Root Sift works even better, and some deep learned descriptors are better than Root Sift in terms of this metric, but not to the large degree. And because it's kind of gold standard now, this Sift and Root Sift, we take this one as a feature baseline. We use mutual nearest neighbor matching. And as additional information, we provide first to second nearest neighbor ratio, this so-called Clover ratio, that method can, for example, PROSAC or deep method can use as an input. So finally, the input for all methods are XY in one image, XY in second image, and the match quality is this ratio. So, and training data is 100,000 image pairs per training sequence. So in total, it's 1.5 million image pairs and different number of correspondences, each depending on hardness of scene. Test data is all the image pairs per sequence divided by 2, because it doesn't matter really the ordering, because we have mutual nearest neighbor. And the training data and the test data without ground truth was sent to all deep learning method authors which we could find, and ask them if they would like to participate in our benchmark and tutorial and so on. So because one thing is this, some method can be better because the method is better, or it can be because people used the better data or more data. And this is one of the things which you probably don't need to take this benchmark results as a kind of final word, because maybe for some methods this amount of data, 1 million, is insufficient, and if you scale it 10 times, the ordering would be different. We'll see. We are planning to extend this benchmark. So let's start with the classics. We assembled a bunch of different like classical models. First is Scikit image. RANSAC, it's vanilla RANSAC implemented in pure Python, plus least squares fitting. So this is exactly original RANSAC paper we would suggest. OpenCV RANSAC, which use, unlike Scikit image, 7-point solver, and also has improved least squares fitting, so it's used 11-bar algorithm for fitting. Least medians, it's very simple classic algorithm, and locally optimized RANSAC in our implementation, which is available by PyDig and SAC PyPy package. Also, we used advanced methods, which were described by Ondra and Daniel and Irji. So DegEnSAC, and one which estimates this degenerate case, GC RANSAC, MaxSAC, MaxSAC++, USAC, a contrarian RANSAC, and the combination of those which were implemented by Daniel in very recently, to see how they work together. What we are not included, first, affine RANSACs. For example, as we were mentioned, you can solve epipolar geometry with just 2 affine correspondences. It would be much faster, but this would require additional information, like local affine frames, and some detectors don't provide them. For example, like even from SIFT you can have like scale and rotation. It's not completely affine frame, but kind of. But for the superpoint you have only X and Y, and superpoint works well. So another thing which we haven't tried, the Colmap RANSAC and guided matching methods because of lack of time. Deep learned method, we used DFE by René, context normalization and ACNI from EPFL and Google, NMNet version 2, and OANet. We haven't included several learned methods, specifically superglue, as it looks like it's a super great method, but it used much more data than the rest method are. Basically, superglue learns additional, like improved descriptors and key points based on all context, all key points, and all descriptors from both images, which is definitely that none of other methods doing. Then NGRANSAC and 6D convolution method, just by lack of time, authors cannot train that in time. And we did like ask them only like months before, so not really much time train. And eigenfree training method, unfortunately, authors haven't answered to us. And a year ago, I have did a Twitter poll, is which RANSAC do you use, especially when you go for Python? And people use, okay, it's OpenCV. Why should we use something differently? And is it a good idea or not? So let's see. This one is, first, let's take standard thing. Okay. Well, step before. So what we did is additionally to set all the methods kind of on the same ground. We haven't fixed the thresholds or the same threshold or confidence or anything else for the all methods, because, for example, one method would require different hyperparameters and so on. Instead, we use our training and validation split to actually kind of learn these parameters, which means that just like grid or random search over possible values of the RANSAC inlier threshold, of the some internal parameters, and so on. So one cannot say that they're using the same parameters, but one can say that they get the same amount of care and tuning and attention, which is we took those hyperparameters which works the best on the validation set. So let's go. Third thing, so the methods are sorted in accuracy, and one thing is OpenCV RANSAC is not doing really well. So I would not recommend it, and Almedians is even worse, which is understandable because the number of like inlier ratio is definitely less than 50%, and the idea that you can guess calibration metrics by using image size, normalize, and then use essential metrics estimation, it basically doesn't work. Okay, it was worth checking. A RANSAC works a bit or significantly better than OpenCV. SK image RANSAC works well if you look at the accuracy, but it is the slowest method, like by 2 orders of magnitude compared to others. So unfortunately, we haven't been able to get it with like 100K iterations. Then DiggNSAC is actually provides quite big improvement. And then in this kind of similar results, we have MaxSAC, MaxSAC++, GC-RANSAC, and this kind of combination. So if you take GC-RANSAC, so you use this spatial coherence, then you add this degeneracy constraint, it helps a bit. And then you add this MaxSAC++ procedure, it helps even more. So why have we put everything to the same number of iterations for the benchmark? Okay, there are different options to do this, and in our archive paper, in ETO, we actually use different setup. So we take one Google Cloud instance, measure time, and find the number of iterations to fix the time budget. And you can see actually how slow is SK image RANSAC. But the rest are kind of in similar plus minus category of speed. And this is quite hard to tune if you don't have the cloud instances, because we did our benchmark on our machines in our different labs. So we just say, okay, we would not measure the time, we just fix the number of iterations and think that, okay, implementation is important, but probably can be optimized and so on. So, and by the way, you can see that optimal inlier ratio, so inlier threshold is different for different kinds of RANSAC. So for MaxSAC, for example, you need to put this threshold higher, for other RANSAC smaller, and this is very specific for each method. And here, as you can see, that GC RANSAC, and this study was done before this tutorial benchmark, is actually worse, unlike previous results where it actually dominates GC RANSAC. It is worse than both DiggNSAC and MaxSAC, and the reason that here for this graph we tuned only standard so-called hyperparameters, which is inlier threshold, and I guess it was confidence, and that's it. So, and the GC RANSAC has additional this special coherence term coefficient, which influence result quite significantly. So if you tune, you should tune everything. Okay, the question is, does it really matter which threshold do you use to compare the method? And the answer is no. And typically, if one method is better at some threshold, it's going to be better at all the rest thresholds as well. And by the way, the OpenCV RANSACs, except homography, has fixed hard-coded max iterations to 1000. It is now fixed in the GitHub repository. It's the latest version, but as far as I know, it's not yet available from Conda or pip. So if you do pip install OpenCV, it looks like that you would have like quite inferior RANSAC. Just in addition that it is far from optimal for the same number of iterations already compared to DegenSAC. This is also, you cannot go better than this. Okay, let's increase number of iterations. And we also have here results for two other kinds of RANSAC. One is a contrary RANSAC, and we run it in two modes. First is the kind of advertised mode in the paper that this is a contrario and you don't need to tune any thresholds. And as you can see, this is not true. If you don't tune threshold, it performs quite bad. If you tune threshold, it performs quite well. As the same as low RANSAC, and basically this contrary RANSAC is low RANSAC as well, so implementation is good, but it still needs threshold tuning. What's also interesting here that USAC, which is supposed to have DegenSAC inside and lots of other advances, is actually worse than the standalone DegenSAC, probably because of implementation issues. And this thing you will actually notice in different things as well, in different problems as well, for homography or for essential magics. Now, how actually does it really matter how many iterations do you set? And well, to some extent, for the DegenSAC benefits the most from the increasing number of iterations. But I would say that probably this accuracy increase might not be worth 100 been in worst case 100 slower. But anyway, it's kind of helps. So now learned methods. And for learned methods, so we asked authors to provide this without like RANSAC estimation, and that they were trained on everything, and then here are results. And interestingly, that ONET and ACNE is much better than the earlier approaches, but is worse than the state-of-the-art RANSACs like MAXAC++ and GC DegenSAC. ADALAM is a very recent approach which is not learned. So this is handcrafted method which do basically similar things to what deep learning methods do. And it was not that really tuned, unlike the others, because we asked like just 2 days before tutorials, there was this paper, and we asked it author if they could run on our data. They agree. So here are results, and probably this is kind of lower bound of what it can do. And what's the most interesting part, that if we combine these deep learning methods with RANSACs and treat them not as a robust estimators, but instead as a correspondence pre-filtering, like more sophisticated version of Slovak criterion. And the interesting thing is first that the difference between them now, it's not that huge as you could see with DLT, which is least squares. And second is that ordering of methods changes, that DFE and ACNI is better here as a plain correspondences. Probably they are more precise, but they have less recall than OANET and ACNI, which actually improve quite a margin on top of RANSACs. So maybe they are not competitors, maybe they are best friends, classic methods and RANSACs. We haven't tried to pair all RANSACs with all deep methods because it's quite significant amount of computations, but maybe we will do this later. The least squares is not good enough. Maybe one could go for iteratively weighted least squares on top of deep correspondences, and then some small RANSAC loop, which is kind of very similar to what MAXAC is doing, MAXAC++, which samples and then do these related iterative least squares. But instead of PROSAC sampling plus knapsack, we can use these deep methods and integrate them, and I think it should work even better. And the degenerate solutions are the big problem. Now, maybe they are not kind of problem of like general world, but it can be artifact of our dataset, which is phototourism, which is like famous landmarks, mostly man-made structures like buildings. They often have dominant planes. We also have one or two statues, which probably not that dominant planar, but still, if you cannot survive the general problem, then you're in trouble here. But maybe it's not that important for some other cases, like, I don't know, for trees or other kind of things. So to conclude this part, that deep methods are not replacements for RANSAC, they should be used together. They are replacements for pre-filtering. Implementation and algorithms of RANSACs really matter. And please, please, please don't say in your paper that we use RANSAC and don't state any implementation or source code or whatever, because actually, as you could see, that RANSAC results could vary like almost 2 times for the untuned OpenCV to the some tuned state-of-the-art GC RANSAC or MAXAC. And I don't recommend Skimage. It's great because it's pure Python, but just because of this, it's super slow, like practical. And implementation also matters. This is like our probably biggest surprise why USAC, which actually supposed to be the RANSAC before like latest method, why it's actually worse than just some more plain versions. Now let's go for the essential matrix estimation. We test a bit less number of methods, because one thing is not all packages implement 5-point solver, which requires a solution of 10-degree polynomial. So it's a kind of probably not the easiest thing to implement. And SKI image RANSAC, they just avoid this, say, okay, for essential metrics, we still use non-minimal solver 8-point, and that's it. And the rest are the same. And the learned methods are again, the same again. So here, what we see that it's a very bad idea to use 8-point solver for essential geometry. Essential matrix estimation, but here you actually don't see that huge difference between OpenCV, MAXAC, GC RANSAC, or whatever. There is some, so the best one is 62% accuracy, and the worst one is 58. But the difference is much smaller than for the fundamental matrices. If we increase number of iterations, Then again, we have USAC and AC RANSAC is the very last moment. That's why they're not in the previous slides. Again, we see the same thing for the not tuning for threshold. If you don't tune, you lose. And again, USAC is performing quite bad, I would say. Now, does it matter to increase your number of iterations and see the scale of this graph? So this is very zoomed in and the difference is quite small. So probably if you cannot solve problem with Y and K iterations, you should not try that more. And here is actually that MaxX++ works really well here. Again, similar picture for the learned methods. So Acne is the best here. But what's kind of surprising that despite being very bad, the like original context networks, the very first deep learning methods, when combined with RANSAC, it's actually better than more sophisticated Acne. This is kind of surprise for me. And then what we checked, does it really matter to have a best RANSAC or just RANSAC would suffice? So here is OpenCV and MaxX++, so you can see the difference is like 4 percentage points. And here all the methods are used with OpenCV RANSAC. And then we use MaxX++ and get some a bit improvement. But maybe we are now constrained by features, I don't know. So it's also interesting thing to investigate. Again, the conclusions are very, very similar for the essential cases, for the fundamental, except that OpenCV here works pretty well, so you can just use it and that's it. Now I'm going for homography estimators. There is two problems with it. One is that there is no large scale and diverse real world homography data set, because if you think about it, it's usually it's kind of planar photos or graffitis, because in real world, even if you have dominant plane, they are also the correspondences still would be on some other structures, and for homography, because if it's a rejection problem, you can generate almost perfect ground synthetic data as done in methods like MODS or ASIFT. But the drawback is that you don't measure how good your deep learning method would be. You're probably measuring how good and how lucky your data generation method would be to match the distribution of the homographies in the test set. So we don't evaluate deep methods here. We only evaluate classical ones. And because the scale is pretty small, so but we don't need a training set, we split the validation and test split. And you can see that these H-patches sequences data set is the same, the original for the getting these H-patches. So H-patches data set is for the descriptor comparison, and it has additional artificial noise on patches extracted, and the sequences, they are just original images, as you can see here. An extreme view data set, this is mostly taken by me for testing like super extreme view change problem, that when you have, for example, one image from the below and one to the side, so this is a very, very hard problem, but the data set is super small, especially by current standards. So here we use different types of features. For H-patches, it's the same 8K received features extracted and then mutual nearest neighbors match. And for EVD dataset, we use MSCR plus received and Hessian-affine plus received features on the synthetically generated viewpoints, which are generated by MODS methods, which with view synthesis. Otherwise, the descriptors don't match, and you cannot match those images at all. And now with these synthesized things, you can match it. They are still very hard problems, but they are kind of solvable. And the accuracy, because we don't have intrinsic parameters, is mean average accuracy at 20 pixels for projection error. What does it mean? We reproject pixels from image 1 to image 2 by ground truth homography and by estimated homography, and we measure the error. And then we average this error over commonly visible area. And commonly visible area is done by the mask of the size of first image. We reproject this mask and then reproject it back, and what is outside of the image is zeroed out, and then we average over all this visible area, and then say again threshold that is average error is within the threshold, then the homography is correct, and otherwise it's not correct. We evaluated quite a few methods, mostly the same packages and algorithm as before, with except that we have this raw algorithm, which is like speeded up estimation of homography. And that's it. So how it works? Again, AC RANSAC without filtering works pretty bad. List medians doesn't work well. USAC, again, it's the worst method in terms of accuracy, and SK image is kind of good, but still very, very, very slow. OpenCV RANSAC performs pretty well, and it's just worse than LO RANSAC, which is used inside the DegenSAC, but without these degeneracy constraints. And probably this is because of implementation differences. And the best is GraphCut RANSACs. For 10K iteration, the picture doesn't really change. And for 1 million iteration, somehow MaxAx gets better, but again, doesn't really change. And here is everything in one slide. Should you go from 1K to 10K or 1 million? I would say that it's worth it to go in for 10K, but doesn't worth it for going to 1 million iteration. It's super slow. And again, for a game which you weren't even able to compute this in time. Age summary. So here, it's again, it's quite similarly to previous one. Don't use USAC, schema RANSACs, and again, performance it's very important to have the best RANSAC, or at least specify which one did you use. And of course, if you use some non-tuned RANSAC, then you can report that the results are super bad compared to some new deployed method. Regis point cloud registration, that is probably the least kind of worked part of the presentation. We used a couple of data set, and unfortunately we haven't time to get like really large scale estimation, and due to small size of data set we use, and there is because they are very different in terms of size and so on, there is no validation test split. So basically what we done here is kind of what I was criticized at the beginning. So we evaluate on the very same data set as we kind of tuned parameters for, except we haven't really tuned parameters, we use kind of reasonable defaults. But this is probably least reliable part of data sets, part of benchmark. But there is still one or two important results here I would like to share. And for metrics, mean rotation error in degrees, translation in meters, and time. and we used RANSACs with this ultra layer removal method and a couple other algorithms which TJ presented. So one thing is, so for small scale problems, that you could use the outlier rejection with RANSAC or without RANSAC, and it doesn't really matter if you have kind of clean data. But the cost of doing algorithmic method like Gore or branching bound can be significant, and for like clean RANSAC, and it can be very fast. So if your data set is kind of clean, then you can use RANSAC and be happy. This is for the RGBD objects dataset, so the similar story. Unlike that's the branch and bound, this is one of the most precise methods without any pre-filtering. Again, probably because of the size, because it's tractable to run it. And here is runtime. And what is important here that while you can be kind of plus minus precise with plain RANSAC, if your inlier ratio not that great, you will spend more time doing this RANSAC than if you would clean the data and run the RANSACs. So this outlier pre-filtering is a good thing, and this is especially if you take the more large-scale data set, the EGP data set, that we were not able to get any results, like any reasonable results from RANSACs, regardless of how sophisticated they were, like MaxSAC++ or GC RANSAC, without outlier pre-filtering. So it's the main message here. And the runtime is basically dominated by the inlier pre-filtering, outlier pre-filtering method. So go there. And there is no cheap method of pre-filtering, and there are some like descriptors for point clouds which you can use. A lot of them are deep learned, some of them are handcrafted, but none of them, as far as I know, is as good and as precise as for the 2U machine like Loveless ratio. So it's a good place to put deep learning methods as pre-filters, and one of these was presented by René. Unfortunately, we haven't tested it yet here, but we are going to do. Now, this is area which receives actually much less attention than 2U matching because it's harder, it's not that common, and so on. So this is where you actually can get a big improvement by using deep network for training. So overall conclusions, so is that you cannot really do robust estimation without RANSAC. If you check results for all the methods, usually you cannot filter out enough outliers to just use least squares or least median squares or even iterated reweighted least squares. You still need to do some robust estimation. Second, we really need the large-scale data sets for training and evaluation, and we need strict protocol to go forward, because as I show that, like for example, USAC in their paper looks great, but it's probably because of the evaluation artifacts. Because there is no training set, there are no defined metrics, and so on. And what I would like to mention also the story from the different area in the deep learning, in deep metric learning, there is a recent paper by Kevin Musgrave, which named Deep Metric Learning Reality Check, and it basically shows that all the most methods from like last 10 years, if the methods from 10 years ago are tuned properly, then not that worse than the so-called state-of-art methods. That's why the proper benchmarking, proper evaluation, and protocols really matter a lot from progress. Otherwise, we can publish papers for years and then realize that nothing of this works in practice. And as a concrete advice, use GC-RANSAC and deep pre-filtering methods. And as a part of this effort, there are Python bindings to the different RANSAC methods, and PyDigInSAC is actually available via pub install without any compilation of source code. And we are planning to also put MaxSAC++ with GC-RANSAC, with everything, which you can just do pip install without any C++ or Fortran compilation, and just use it like the best method in your work. And if you have any questions, I would be happy to answer.
Okay, yeah, I think if there's no questions, then we can thank for you attending this tutorial, and I hope that you enjoyed all the talks. The video, by the way, in the meantime, we are still checking the chat, so if you write something, we answer, Dimitri will answer. So we will upload the videos, the recorded videos of this Zoom meeting to our website, which you can find also in